Yes, let's start. We are discussing about the nucleophilic substitution reactions. There are two types of nucleophilic substitution reaction. One is SN1 reaction, another is SN2 reaction. We are considering a tertiary alkyl halide here. A tertiary alkyl halide, if it is attacked by the nucleophile, in step 1, the bromide ion leaves the spot so that the carbon gets a positive charge here. What you are creating is a tertiary carbonium ion. Once the tertiary carbonium ion is formed, the nucleophile that came for the attack attacks the carbonium to form the new product here. So we can see the SN1 is following two steps here. SN1 follows two steps here. In step 1, it created the carbonium. In step 2, the nucleophilic attack happened. Among these two steps, the slowest step of the reaction will be the rate determining step. Consider there are two people who are walking. This person can walk in the speed of 10 km per hour and this person can walk at a speed of 20 km per hour. But they are just walking together. So this is A and this is B. They have to reach a final destination. Who will determine the speed, final speed?
The step 1.
Obviously A, because he is a person who is going very slow. So that's, with the respect to slowest person only, you can say, okay, at this speed they can come and reach this final spot. Same logic, yes. Two steps are happening here. Step 1, a stable carbonium is formed. Step 2, the nucleophilic attack has happened. So in step 1, this is the slowest step of the reaction according to chemical kinetics. So therefore, this is the rate determining step. The rate at which the complete reaction will happen will be determined by the slowest step of this reaction. I mentioned that very keenly. I mentioned tertiary alkyl halide. The reason is that when this bromide ion is leaving, it is going to create a carbonium ion. We know the stability of the carbonium ion order. Primary is the least, followed by secondary, and tertiary is the highly stable one due to the hyperconjugative effect. That is the reason we have written tertiary alkyl halide is the one which favors the SN1 reaction, because SN1 follows the carbonium pathway, and whichever is going to form this carbonium, that will be the favorable alkyl halide for us. Now, when you're deciding about the rate of the reaction, though two reactants are here, alkyl halide is also here, nucleophile is also here, but who is determining the rate of the reaction? Alkyl halide is determining the rate of the reaction. You can see nucleophile is not coming into the play at all. What is the number that is written on this Rx? If nothing is written, it means it is 1. So this 1 corresponds to a term called as order of reaction. We have a chapter called as chemical kinetics where we will learn about it. Order of the reaction typically tells you if many reactants are participating, which reactant in what quantity is going to determine the rate of the reaction. Since I wrote 1 on the top of Rx, I understand among these two reactants, only this is deciding the rate of the reaction. And such reaction will be called as first order reaction. Consider I am writing rate of reaction is directly proportional to A power 2. Then I will say the order of the reaction is 2. Here I write 1, so I call it first order reaction. Now you can understand why it is called as SN1. The one that is written on it tells you about the kinetics of the reaction here. Understood till this?
Yes, sir.
Let's go with our NCRT now. We are discussing about the nucleophilic substitution reaction. SN1 reactions. Look at this. They have taken tertiary alkyl halide and a nucleophile is coming for an attack. What has happened? Step number 1. The tertiary alkyl halide is in equilibrium in step number 1 because you're forming it's the slowest step. So definitely it will put up an equilibrium. Br minus left, so you created a carbonium ion. This carbonium ion is attacked by the nucleophile to form the final product here, right? So SN1 reactions, look, take the next one, is generally carried out in polar protic solvents. What do you mean by polar protic? Consider water, H2O. Here, this is polar because oxygen is negative, H is positive. It is also protic because you know that it can release H plus ion. So those solvents which are having charge separation can also release H plus. Such kind of solvents are called as polar protic solvents. So the examples are water, alcohol. We know alcohol where you are having ROH will release RO minus plus H plus. You can see polarity is there and H plus also it releases. Acetic acid, CH3COOH, where it can release H plus, isn't it? And you know it is polar also. The reaction between tertiary butyl bromide and hydroxide ions yields tertiary butyl alcohol and follows the first order kinetics. That is, the rate of the reaction depends upon the concentration of only one reactant, which is tertiary butyl bromide. This occurs in 2 steps as we mentioned it here. Step 1, the polarized CBr bond. Look at the word polarized because bromine is negative, carbon is positive. It's already polarized only. It undergoes a slow cleavage, very slow. That's the reason you have equilibrium here to produce a carbonium ion and a bromide ion. The carbonium ion thus formed is attacked by the nucleophile in step 2 to form the substitution reaction. Step 1 is the slowest and reversible. It involves a CBr bond breaking for which the energy is obtained through solvation of halide ion with the proton of the protic solvent. What do they mean by that? How do you break this? The CBr is there. You know it's a covalent bond. How do you break this? You need energy for that. You can see the CBr once this halide ion, once I have the CBr, I break it and I leave the Br minus out. This Br minus is involving in a solvation. What do you mean by solvation? That means it is getting surrounded by the protic solvents. Solvation is the process in which the ions are getting surrounded by water. So he is obtained by the solvation of the halide ion with the proton of the protic solvent. Because the solvent is protic, right? So it is giving the proton of the protic solvent is solvating this halide ion here. Since the rate of the reaction depends upon the slowest step, the rate of reaction depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide. Definitely, more is the stability of the carbonium ion, more will be the ease of the formation of the alkyl halide. The immediate alkyl halide attack will happen, isn't it? And faster will be the rate of the reaction. In case of alkyl halide, tertiary alkyl halide undergoes SN1 reaction very fast because of high stability of tertiary carbocation. So we have studied SN1 now, where you can see tertiary is greater than secondary, then primary, then methyl halide. For the same reasons, allylic or benzylic shows high reactivity towards SN1. If you say carbonium is the one which is giving you the determining the reaction, then definitely allylic carbonium ion, benzylic carbonium ion will much more stabilize this SN1, isn't it? That's what the reaction is showing you. For a given alkyl group, the reactivity of the halide. Look at the reactivity of the halide here. Important question for 1 mark. reactivity of halides, because iodide is a very good leaving group. That means when I'm using Ri, immediately, let me say I'm having Ri. To this, a nucleophile is coming for an attack. To this, a nucleophile is coming for an attack. If this iodide is easy to leave faster, only then the nucleophile can come and attack, isn't it? So that's the reason this order is provided to us. Ri followed by RBr, followed by RCl and RF. Understood till this?
Yes, ma'am.
Right. We are discussing about the stereochemistry point of view here. Discuss about SN1, SN2 here. So let us consider the stereochemistry of the SN1 reaction. In the case of optically active alkyl halide, what do you mean by that? That carbon which is chiral in nature. The carbon which is chiral in nature will be optically active. So look at this carbon. This carbon is surrounded by 4 different groups: methyl, bromide, some propyl is here, hydrogen is here. So it is optically active. In such reactions, what happens? Step number 1, bromide leaves. You created carbonium ion. This carbonium ion, look at this carbonium ion here. What is the hybridization of carbonium ion here? How many bonds it has made? 3 bonds. So what is hybridization? It is sp2 hybridized. When I say sp2 hybridized, what is the geometry? Trigonal planar. What do you mean by trigonal planar? That means it is on the plane. The nucleophile, the incoming nucleophile, has the ability to attack it from either side. It can attack from this side as well as from this side, because this carbon right now is planar, on the plane. It is no longer tetrahedral. It is on the plane now. So the attack is happening on both the sides. So if the attack is happening on this side, I get the OH this side. If the attack is happening on from this side, I get the OH this side. Now when you look at it through polarimeter, one of the product is positive. That means it is rotating the plane polarized right in the right hand side direction, D form. The another one is rotating the plane polarized light in the left hand side direction, negative, L form. Dextro-rotatory, levo-rotatory forms. Understood till this?
Yes, ma'am.
Right. So can you think the reason why it happens? Actually, the carbocation formed in the slowest step, being sp2 hybridized, is planar, chiral in nature. It is no longer chiral here, it is achiral, because it has become planar here. The attack, why do I say achiral? Because if a carbon is there, if it is bonded with 4 different groups only, you can say it is chiral. It is right now bonded with only 3 different groups. 1, 2, and 3. There is no 4th group here. So I say it is achiral. The attack of the nucleophile may be accomplished from either side of the plane of carbocation, resulting in the mixture of products. One having the same configuration of the OH attaching on the same position as allied ion. What do they mean by this statement? Ma'am, Br was in this side, left hand side. I get 2 products now. You can look at the 2 products. One product is having the OH attached same as bromine. Another one, you can see it is attached opposite to bromine. The attack of nucleophile may be accomplished from either side of the plane of carbocation, resulting in the mixture of products, one having the same configuration, attaching on the same position as the allied ion, like this, and the other having the opposite configuration, like this. This may be illustrated by the hydrolysis of the optically active 2-bromobutane. To explain you, they have what the molecule that they have taken is 2-bromobutane. This results in the formation of plus or minus butane 2-ol. Why do I say plus or minus? Both are possible. So I call it plus or minus So butane to wall. So we can understand that SN1 reaction leads to racemization of the products. SN1 reaction leads to racemization of the product. Two products are possible for you. Clear till this, Ra?
Yes, ma'am.
Right. Let's go for the next process here, which is SN2. Just reverse everything. What are the things that we learnt about SN1 at first? Let's put on all the points. When I said SN1, the first point was that you need a polar protic solvent. What kind of a solvent you needed? You required a polar
Polar protect.
protic solvent you need. You needed a polar protic solvent. You required tertiary alkyl halide. We understood that the slowest step of the reaction is the step number 1 where you created carbonium ion, and the order of the reaction is determined only by the concentration of the reactant here and what kind of product you get. You get racemized product. That means you get both plus or minus forms of the product here. This is with respect to SN1. Now we are moving for SN2. Let's move for SN2 reaction. The word number 2 tells you that the reaction, the rate of the reaction is going to be dependent on both Rx as well as nucleophile. Both are important for us. So if I look at the alkyl halide that I'm taking, CH3Br, it is methyl halide or even primary halide for the term. If I'm having methyl halide or primary halide, if I'm going to take a nucleophile with me, OH minus is coming for an attack. Here what happens is that this CH3Br is like this. The attacking nucleophile comes from the back side and this Br minus leaves out. Look at the geometry right now. Initially carbon made 4 bonds which was tetrahedral. Now when the attack was happening, it is forming a transition state here, not an intermediate transition state. That means very short-lived one. You cannot look at it for a quite long time phenomenally in any kind of spectroscopy. Very short-lived species. Transition state, you can see the nucleophile attack is happening on the carbon and the bond between carbon and bromine is about to be broken. Right now you can see carbon is having 5 bonds. 1, 2, 3, 4, 5. Carbon making 5 bonds. You never have come across this. Carbon always makes only 4 bonds, but here is a transition state. Very momentary period of time this happens, which is trigonal pyramidal, bipyramidal in its geometry. Remember PCl5 you have studied in chemical bonding. 5 bonds made by it, you say the geometry is trigonal bipyramidal. Similarly, carbon here, there's a trigonal bipyramidal geometry here. Same happens here. So what happens? The nucleophile attacks it is a transition state. This occurs in one single step. OH minus comes. This is a transition state that it is going to form. And immediately what you get is a nucleophile attached CH3 here. And the Br minus left it. You can see the attack is coming from the back side. Attack happens from the back side. Just imagine the umbrella that you take in the wind. I'm having an umbrella here. I'm taking it in a wind. Strong wind is there. I'm taking it. Suddenly the wind gushes it inside. So after some time you could have seen the umbrella is going for an upturn like this. Have you seen it? Have you come across this inversion? Inversion of the
Yes,
umbrella.
ma'am.
Yeah. The same typical, it's not realistically, it's not an umbrella or not. Just for an understanding, they are saying. So the umbrella upsided itself. Same logic happens here. For example, if I say I'm having an alkyl halide which is of R configuration. Okay. Your can involve prologue model RS configuration. Imagine I'm going to have an alkyl halide which is of R configuration. Here I can't say whether it is R or S because it is not chiral at all. Let me consider C2H5 is there, CH3 is there, Br is there, H is there. Now the nucleophile is coming for. Is this a chiral carbon? Yes. Now the nucleophile attacks and the Br goes out. Now the nucleophile has got attached it like this, and the Br minus left the place. So if its configuration was R, the configuration of the product that has got formed will be S. You can see it's completely inverted. It was R, now it is S. If it was S, now it would be R here. So this kind of a inversion that you see in SN2 mechanism is called as Walden inversion. This inversion is called as Walden inversion. So what are the points that we have to understand about SN2? The rate of the reaction is determined by both alkyl halide and nucleophile. If you mentioned it was polar protic solvent, here it happens in polar aprotic solvents. They are polar only, but they cannot release H+. A very common example is DMSO, dimethyl sulfoxamide. DMSO, DMF, dimethyl formamide, acetone. They are all polar, but they are aprotic. They can't release H+. And we mentioned that I'm taking methyl halide here. The next point that we have to remember is that SN2 favored by less hindered alkyl halide. Usually methyl or primary. This will undergo SN2 reaction. Shall I change the screen?
Ma'am, one second. Ma'am, but this one can also react with the protic solvents or only aprotic?
Only aprotic there. SN2, if you want the SN2 reaction to happen, then polar aprotic only will modulate it. Because when you use polar protic solvent, that will lead to the formation of this ionic carbon. That means carbocation.
Okay, ma'am, done.
Yes. So we are discussing about the SN2 here. Look at this. You can see there is an alkyl halide here. OH minus is coming for attack. You can see there is a transition state, the one that is written in the square bracket. You can see that. And the chloride left, you get OH. You can see there is only one product that is getting formed here. In SN1, you saw two products were there. Here there is only one product here. So the reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows a second order kinetics. That is, the rate depends upon concentration of both the reactants. Both of them are important for us. Alkyl halide as well as OH minus. Both are important. The above reaction, they are just depicting to you in this solid wedge manner. I'm just skipping it. I'm skipping this as well. As the reaction progresses and the bond between the incoming nucleophile and the carbon atom starts forming, The bond between carbon atom and the leaving group weakens. We already learnt it, isn't it? This bond is getting strong. This bond is becoming weak. As this happens, the three carbon-hydrogen bonds of the substrate start moving away from the attacking nucleophile. Look at this here. Initially, these were the three hydrogen. The yellow colored balls are their hydrogens here. Hydroxide ion was approaching. Once it was approaching, you can see now they are arranging themselves, so they are moving away from the hydroxide ion. Initially, they were all approaching right in the same direction of the hydroxide ion attack. But now after this, you can see they are all taking the different orientation in order to avoid the repulsion between them. You can see the bond is getting elongated here. That means it is getting weakened. In transition state, all the three CH bonds are in the same plane. Look at this. They are all in the same plane here. And the attacking and the leaving nucleophiles. Attacking and the leaving are partially attached to the carbon. You can see we have drawn only the dotted lines, saying that nothing has got completely broken, nothing has got completely formed also. As attacking nucleophile approaches closer to the carbon, CH bond still keeps on moving in the same direction till the attacking nucleophile attaches to the carbon and leaving group leaves the carbon. Until then, they are completely getting attached or getting left out there. They keep on moving in the same direction only, same kind of forces happening on them. As a result of configuration is inverted. It has got inverted. The carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind. This process is called inversion of configuration. This is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms here. And that's the reason we call it as trigonal bipyramidal. Understood? Here,
Yes, ma'am.
since this reaction requires the approach of the nucleophile to the carbon bearing the leaving group, the presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect. Of course, we say the OH minus or the nucleophile is attacking from the backside attack. If this carbon is going to have some bulky groups, methyl is there, ethyl is there, propyl is there, it's very difficult for this incoming nucleophile for the attack. Definitely it will inhibit the effect here. Of the same alkyl halide, methyl halide react more rapidly in the SN2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are least reactive because the bulky groups hinder the approaching nucleophiles. Thus, the order of reactivity for which mechanism? We are talking about SN2 mechanism here. For SN2 mechanism is methyl, ethyl, isopropyl, and tertiary butyl. You can look at the values. They are showing you the rate, how much they will react. Understood, Ra? Let's go for the stereochemistry of them again. Yes. In case of optically active alkyl halides, again I have a carbon which is having 3 different groups that is attached here. Okay. Formed as The product formed as a result of SN2 mechanism as an inverted configuration as compared to the reactant. This is because the nucleophilic attaches itself on the opposite to one and where the halogen atom is present. So when I am having my minus form, that means levorotatory form of 2-bromo-octane that is made to react with sodium hydroxide, you can see it is completely having only one of the type, D form. Positive form is formed. Do you understand?
Yes, ma'am.
Yes. So we discussed about the SN1 SN2 pathway, about the stereochemistries and which determines them, etc. I don't think so. You want me to explain about these things, isn't it? If you have learned it already, let's skip this. Or do you want me to explain it?